have Dr. Guannan Zhang, who is a research staff in Computational and Applied Mathematics Group at Oak Ridge National Labs. Dr. Zhang has studied mathematics at Shandong University in China, and he received his bachelor's and master's degrees in 2007 and 2009. And he has completed his PhD in computational science at Florida State University in 2012 and joined Oak Ridge National Labs right after that as a householder fellow in the Computational and Applied Mathematics Group. And this is within the Computer Science and Mathematics Division. So he has been holding a joint faculty appointment with the Department of Mathematics and Statistics at Auburn University since 2014. His research interests, particularly in the AI space, include high-dimensional approximation, uncertainty quantification, machine learning, stochastic optimization and control, and model reduction for parameterized differential equation. So it's an honor to have him here today to share some of his findings with us. Dr. Zhang, the floor is yours.
Thank you. Thank you for the introduction. And I'm glad to be virtually at UTSA to give this seminar. And hopefully, through this seminar, we can find some common interest and gradually establish some collaborations between Oak Ridge and UTSA. So today I'm going to talk about some of our recent work on like black box optimization, driven by the applications, for example, in a lot of scientific applications, scientific domains, people are using black box optimization, but in the machine learning domain, really, it's been driven by this reinforcement learning tasks. So this is a joint work with my colleagues Guannan Zhang, Dan Lu, and Huang Chuan, and both of them are, and all of them are at Oak Ridge. So please feel free to interrupt me anytime, since it's a virtual seminar, so I cannot see your faces. So I'm just hope that we can do interactions as much as possible. So you can either interrupt me directly or put in the chat. So I have the chat window open on the side of my computer, so I can see pretty much all the messages. And this work is about a new method we developed for black box optimization based on, it's a variant of evolution strategy. So we propose a new algorithm, especially a new operator, to capture the gradient or define a new gradient operator, I would say. So here is the outline. So start with the introduction, set up the problem. And the second part, we're going to discuss, or I'm going to introduce our new algorithm, especially the new operator, and discuss why we think this operator is better than the existing ones in capturing like the global structure of a black box loss function and skipping like local minimum, all these things to find the global minimum. And in the third part, I'm going to talk about some theoretical analysis we did on this operator, but those theoretical analysis is not directly related to the convergence rate or anything in the regime that we want this method to work. Basically, in the non-convex case, this analysis is only for convex case and only to provide some consistency result. See, since we're defining a new operator, we want to see what is it consistent with existing like a local gradient operator, for example. And the next part is about the numerical test on some benchmark high-dimensional optimization functions. You can find a lot of them of different types online in the document. So they are well known and people are using those functions to test benchmark the performance of their new algorithms. And the next part is the application of our algorithm to some reinforcement learning benchmarks that people use in their reinforcement learning research papers. And I'll conclude with some remarks and some future plans. So then the first one is to set up the stage. So what is black box optimization? Means black box means simple, easy to understand, means we have a loss function, but we can only query the loss function, get the function value, and we don't know what happens inside the function f. Oh, by the way, can you guys see my mouse, like the small hand? So I can use that as a pointer?
Yes.
Okay, cool. Thanks. So this is what we're dealing with. So we want to minimize this loss function f of x, and we can query f, but we don't know what's in there. And which means the gradient of f is not available. And sometimes even the gradient is available, it's not very useful, especially in the non-convex case. So if the function is non-convex, using local gradient will get the optimizer trapped in some local minimum, and which will give us only a suboptimal solution. So, and this happens a lot. This black box optimization happens a lot in scientific applications. For example, if people want to use some legacy code that was developed like 50 years or 30 years ago, and it's all compiled, especially in the DOE's mission space. Some of the codes needs to be certified or approved by DOE before it can be used in practice. Once it's approved, you cannot change anything in that code. If you change anything, you need to get reapproval, which will take a long time. So, but people always want to use those code to solve some new optimization problem. In that case, you cannot change the source code. You can only use your existing code as a black box simulator. And quite often, this objective function f will include some of those simulators in scientific domains. And another example is like if you want to optimize like a hyperparameters or the architecture of a neural network, that's then you need to treat the whole thing, the training process, as a black box. And in reinforcement learning, it's even easier to understand in the sense that in reinforcement learning we have environment, which usually is a simulator, and we don't know what's inside the simulator, so we use black box optimization to train the agent in order to solve the reinforcement learning problem. So now, evolution strategy. So evolution strategy in general is a class of method to solve global optimization problems in a black box way. So basically, we just optimize it by setting up a population and gradually evolve that population from by treating the loss function as the fitness of this population. So they gradually improve the fitness of the populations to find the global optimization, the global minimum of the loss function. That's the general concept. And in that sense, it depends. There are many types of evolution strategy algorithms. Some of them requires gradient or some sort of gradient information, and others don't require any gradient information. Just people may heard of like genetic algorithm can be categorized as the one type of evolution strategy. So basically, there are two types, like the population based, or there's a method using serrated gradient. So, and our method falls into the second type. Basically, we want to use some kind of gradient information to guide us to find the global minimum of the loss of a black box loss function. So typically, particularly what we are interested in this work is the class of method based on Gaussian smoothing. So there are two very good papers by Flexman and Nesterov. One in 2005, more on the algorithm side. The other one is in 2015, more on the theoretical analysis side. Basically, in those papers, they say, since we don't have the gradient information of the black box loss function f, and the loss function may have a lot of small fluctuations and a lot of local minima, so we want to overcome those. So instead of optimizing f directly or compute the gradient of f directly, we do a smoothing. Basically, it's just a convolution of the original loss function with the Gaussian kernel. And by doing this smoothing, even f is not differentiable, and the smooth version of f, which we call it f sigma, is differentiable. So, and also depends on the width or the variance of the smoothing kernel, which is the sigma here. So you can control sigma and change to adjust the level of smoothing. So basically, the bigger sigma, the smoother the function, and but you don't want the sigma to be too big, because if sigma is too big, then you don't have any structure of your smooth version. And once you define your smooth function, then you can take gradient of your smooth function f sigma and represent such gradient by doing simple integration by part, and represent such gradient as another expectation of the function f itself. So there's no gradient information needed for f. You can represent the gradient of the smooth function by expectation. And then to approximate the gradient, you just need to draw samples from the standard Gaussian distribution and using, for example, Monte Carlo method to approximate such integral. And once you have the Monte Carlo estimator of gradient of f sigma, you can plug that into any gradient-based optimization method, like gradient descent, or you can add momentum, like plug into Adam algorithm. I mean, whatever, those gradient-based methods. But yeah, so basically people using that in the machine learning area to solve some black box optimization. For example, people just use simple Monte Carlo estimator, like this paper in 2017, to solve reinforcement learning problems. Basically, they just randomly draw samples from a Gaussian distribution. And there are some other versions. The main challenge of this this type of method is the approximation, the accuracy, or the variance of the Monte Carlo estimator of the d-dimensional integral. So think about if d is large, for example, you're training a reinforcement learning agent, and you're using a neural network as your agent. You easily have hundreds of parameters that you need to train. Then this integral will become hundreds of dimensional integral. And you want to use a small number of samples to approximate this integral, and then we'll bring in a big variance, and those variants will almost just kill the performance of your algorithm. That's the disadvantage. So to kind of address that disadvantage, people keep improving it by just doing like some orthogonal sampling of Monte Carlo, or using some past data to infer some important directions in the d-dimensional space, and only sample along those important directions to reduce the kind of like the implicitly reduce the dimensionality of this high dimensional integral. By doing that, they hope they can reduce the variance of the Monte Carlo estimator, so that they can have a faster or more stable convergence or training process. This is that. And yeah, pretty much we'll start talking about the challenges. So the challenges is, and the challenges like a complex landscaping or loss function. For example, if you have a lot of local minimum, then you need to use a bigger sigma, like in this variance, in this representation, the bigger sigma to smooth all this variance, all this local minimum out. But in high dimension, if you use a bigger sigma, which means the support of the domain of the integral is RD, but the high probability region will become bigger and bigger when you in large sigma, and which in high dimensional space will increase the difficulty of approximating such high dimensional integral. So in practice, what people do is, when people use a Monte Carlo estimation of this smooth the function of the integral, they turns out to use very small sigma. So basically, it's not much different from using that integral to approximate local gradient, because people can see when sigma goes to 0, this operator will converge to the local gradient of the original function f, if the gradient exists. So basically, the challenge is the high dimensionality is the most important challenge. If dimension is low, you can use big sigma, smooth out local fluctuation, and get the global optimum, no problem. But when the dimension is high, there is an issue. So then our objective is, since we see the challenges lies in the approximation of a high dimensional integral, then we were thinking, can we reduce the dimension by redesign the operator? Not define the gradient as a directional operator, as an n-dimensional operator, n-dimensional integral, but as some kind of like a lower dimensional integrals. And then we also observe that, if we talk about gradient is really, you wanting to explore n orthogonal directions to get a gradient, to get n partial derivatives, and then in the n orthogonal directions, then you get your gradient information. And also we want to keep this smoothing effect because we want to use this method to solve global optimization to overcome some local minimum. So that's why we want to keep the smoothing effect. Basically, we want to keep the smoothing radius sigma, or the variance sigma, to be relatively large. And we want to reduce the dimension from n to 1D. And then we want to also capture the important, have some concept of gradient information. So that's kind of the motivation of the idea. That's why that's motivate us to develop this directional Gaussian smooth operator. So, and we did some analysis on this and some demonstration. So basically, so the key idea is simple. The reason why they need to approximate a d-dimensional integral to get their gradient is because they do d-dimensional smoothing. And in our setting, so instead of doing a d-dimensional smoothing, we do smoothing along d orthogonal directions in the d-dimensional space. Basically, along each direction, we represent that we use the c to define the direction, and we can represent the function f along that direction as a 1D function. Basically, we call it g of y given x and c. X is the current state of the optimization, for example, and c is the direction. And then we can define a 1D Gaussian smoothing just along the c direction. So then this smoothing becomes a 1D function, g theta. And then we can compute the derivative or represent the derivative of g of theta just along that direction defined by c as this 1D expectation. Okay. And if we define such d of g theta along n orthogonal directions, c1 to cd, and put them together, we have our gradient operator, which is determined by the big c, which is the collection of all n orthogonal directions, and the smoothing parameter sigma, which determines how big the variance of each Gaussian kernel that we use to smooth out our objective functions along each direction. So the difference between this operator and the standard operator in the evolution strategy is each partial derivative is based on a different smoothing, or 1D smoothing. And then I want to show you why it works. So basically, it's just like a simple 2D illustration. So this figure is the contour of a 2D Arclay function, which is one of the benchmark test functions people use to test the global optimization. And you can see there are a lot of local minimum. And this black star is the global minimum. And right now, we assume we are standing in the center, in the middle of the domain, and we want to find which direction we want to go next step. And if you compute the local gradient at this point, center point, then the blue arrow is the local gradient direction. Of course, it points to a wrong direction. If we follow this direction, it will take us a long time to come back to the right direction. Sorry. And it's because if we, on the right and on the top, the blue curves are the cross sections, 1D cross sections of this loss function along two direction x and y axis. So you can see because it has local minimum and fluctuation, that gave us the wrong gradient, local gradient direction. And if we do smoothing first along each direction, x and y, and we get this orange-like curves along those directions, along each direction, and we compute the partial derivatives along each direction and put them together to formulate our gradient direction. You can see this orange curve almost pointing to the right direction towards the global minimum. So, and the reason why is because it smoothed out the local fluctuations and captured the global structure towards the global minimum. So here I want to point out this is that, so our method, we didn't anticipate it works for all the landscapes of the loss functions. So it's suitable for those landscapes or loss functions that has some kind of global structure, like a convex structure, but perturbed or added with like a significant amount of local fluctuations or local modes, like this actually function is one example. If a function, a loss function, does not have any global structure, we don't expect our method can work. Actually, we have some examples or tests to show that our method doesn't work well if the loss function does not have some sufficient or some good global structure to capture. Anyway, so this is the kind of like 2D illustration. Hope that will help you understand. And then this is another one, basically it's like just in a bigger domain. So we, instead of plot just one pair of arrows, we plot a bunch of pairs of arrows. Basically in here, I want to show this is also actually function. You can see the contour represent a lot of local minima. And we plot both our local gradient in the blue and our gradient in the orange. And on the left, we set our smoothing sigma to be very small, like 0.01. Basically, by doing that, we see our gradient direction is almost the same as the local gradient direction. And in fact, if we let sigma goes to 0, our operator also converge to the local gradient operator if the local gradient exists for that loss function. And as we enlarge the smoothing radius sigma to 1.0, so we can start saying the blue arrows, oh no, the red arrows are start pointing to the center, which is the global optimal, which means the red arrows start capturing the global structure of the loss function. So here's another, this is just another illustration. And the advantage of define the gradient operator this way is because now we have, instead of for one high-dimensional integrals, we have a bunch of 1D integrals. And those 1D integrals are much easier to approximate with high accurate method. So in this case, since we're using Gaussian smoothing operator or Gaussian convolution for each 1D integral, then we're using, it's a natural choice to using Gaussian Hermite quadrature rules to approximate each component or each partial derivatives of our gradient in our gradient operator. And as we all know, this Gaussian quadratures give us spectral convergence. So which is much accurate, more accurate than Monte Carlo estimator. And which means we only need to use a very small number of samples along each direction. Get a good approximation. So then what we do is we just replace each component in our gradient operator with its estimator based on Gaussian Hermite rule. And after that, we have our estimator of our gradient operator, or we call it DGS gradient operator. And then we just plug it into any first order gradient based algorithms. So we did test like a simple gradient descent, like Adam, and several other types of algorithms that in building like TensorFlow and PyTorch for training like neural network models. And also, if you, I mean, since we only explore n-orthogonal directions, you might think, okay, maybe the choice of the direction are not good enough. So, I mean, to resolve this issue, so we kind of add some randomness into the into the selection of the n-orthogonal directions. So basically, we can introduce some random perturbations to the selection to the orthogonal system. For example, we start with the Cartesian system, and we can gradually add in some noise or small perturbations to the original Cartesian system to try to do a more exploration or random exploration in the high dimensional space. But I have to say, in high dimensional space, those random perturbations is not very, I mean, it depends on, it's problem dependent. If your function is very rough, like what are some of the functions that I will show you later in the test, maybe some random perturbation will kill the algorithm. So I'll show you later what I mean. But for some functions, adding those random perturbations is helpful. Anyway, so here is just a summary of our algorithm. And basically, at each time step or each iteration, we just evaluate our Gaussian points along those orthogonal directions, and then we assemble the partial or the directional derivatives using Gaussian quadrature rules, and then we put them together to formulate the gradient information and put the gradient information into some gradient-based method. Here we just use the gradient descent, but we can easily incorporate a momentum-based method or introduce like a linear rate decay schedule into our algorithm, which happens to be very helpful to our methods. So, and then we can do some random perturbations if we need to. And some theoretical analysis or simple analysis. So basically, this analysis, as I pointed out at the beginning of the talk, is not to analyze the performance of the algorithm in the scenario that we have a relatively large sigma, so we can solve the non-convex problem. It's just to provide some consistency result to see when sigma goes to 0, our methods will converge to the local gradient. And also the performance of our algorithm will be comparable to existing like a local gradient-based algorithms. So that's the purpose of the analysis. Since we're defining a new operator, so a natural question will be, is your operator consistent with the existing ones in some scenario? So that's the question we want to answer. And the first lemma we put in here is, so when sigma goes to 0, so what's the difference between our estimator of our gradient operator with the true local gradient? You can see the error consists of two parts. The first one is the approximation error from the Gaussian Hermite rule, and the second one is the smoothing error. So basically, we have two parts, right? The first we smooth it, the second we approximate it. And you can see as sigma goes to 0, so both errors are gone. So this is just the first lemma to show. And if we just look at how good our method in approximating local gradient, forget about the non-local ones, the big sigmas, just to see in the purely local setting. So how does our operator compare to other ones? So in the local setting, to guarantee a good accuracy for the local gradient approximation, as pointed out in this paper in 2019, no method can beat finite difference, basically, in terms of the step size, basically the sigma, and the number of samples. In terms of number of samples, finite difference only needs that. A center sample plus the forward step samples, and that's it. But our method instead requires, we can share the same sigma, the step size, but it requires another log d over epsilon square number of samples. So if you only care about approximating local gradient, then our operator is not a good choice. Finite difference is the good choice. And even the standard like Gaussian smoothing strategy is not a good choice either, as you can see. You either requires more points because it's obvious because they use Monte Carlo estimator, which leads to this 1 over epsilon square factor in the number of samples that is needed for both the Gaussian smooth and the sphere smooth. The sphere smooth is just you don't draw samples you only draw samples on the sphere with a fixed radius. So basically, this is the message that if you want to use the operator to approximate the local gradient, it's not a good option. But at least we have some consistency result. And now, in terms of the performance of our algorithm in optimizing convex functions when sigma is small. So because if the function is convex, then local method will work. You can use the gradient, local gradient to get the drop down. So here is also to provide some consistency result. So we see this is our convergence rate analysis for convex functions when sigma is small. And here is the comparison with like a random search, like a Nesterov's method, which is one of the benchmarks that people, baselines that people use to compare. So basically, you can see this is our method. So to guarantee this convergence, this is the radius that we need to use. This is number of samples, and this is number of iterations. So what I want to point out here is, if you really look at the number of samples, our method requires more than what Nesterov's method needs to achieve the prescribed accuracy epsilon in the optimization for convex functions. However, our iteration number is much, much smaller than Nesterov's methods. In fact, the number of iterations is independent. We prove that number of iterations is independent of the dimensionality, which is a good thing in the sense that even we require more samples, which means for each iteration we need to use more samples than Nesterov's method. But those number of samples or those function evaluations can be totally parallelized. So if you have a cluster, you can run your all these samples on the cluster and using a parallel computing system, a distributed computing system. And what cannot be parallelized is the sequential iterations, is this number of iterations. So those iterations has to be run sequentially. So which means for example, in some optimization problems involving complex models, like reinforcement learning, for example, if we have a supercomputer or a cluster, we can our method can fully exploit the computing power of a supercomputer. But Nesterov's, they are purely sequential, pretty much. You can see the number of samples in each iteration, they only run one sample. So number of samples equal to the number of iterations. This purely sequential process is not very good in training complex models because you need to wait a long time. So there's always a trade-off. Let me see. Okay. So then the experiments. So we have two sets of experiments. The first one is using like a benchmark test functions, like based pretty much in a non-convex case. And to demonstrate our performance, we have like lower to medium dimensions and also very high dimensions, like 1,000 to 2,000 D. And we have like a kind of like a real world example design problem. But this problem is quite simple, so probably doesn't show much advantage of our method since it's relatively low dimension. And the second set of examples, we are going to show like performance of our algorithm in some reinforcement learning tasks and compare with some standard baselines. We compare with 6 or 7 other baselines, pretty much. So the first set of example is functions. So actually, you can see the actually function. Those are the 2D plots, but we tested in 10D, 1000D, and finally 2000D. So the feature of the active function is that it's very highly concave. So it's very flat in the most of the regions in the parameter space, in the search space, and the global mode is very small. So basically, if you use a local gradient method or any method, the gradient is very, very small in most of the regions in the search space. It's hard if you start from the corner, one of the corners in high dimensional space, it's hard to find the global mode. That's what most global optimization method will struggle with. And for this one, the Ross-Trigan functions is another example. So this function has some global structure. Basically, there is a quadratic structure underlying. You can kind of see it, but the local fluctuations are much, much more dramatic than the noise should be. So in fact, this function is hard. The only way we can optimize it to exploit it has something like a separability structure. So basically, this function is defined by adding those 1D functions, fluctuation functions. So basically, if you can exploit the separability, then you can optimize the high-D function like 1D after another. But we don't know that in practice. So we just assume, we just see this, the purpose of this function is to test if a method can exploit those separability, if the separability exists. And this Levé function is similar, like non-convex lot of local minimum. And finally, we want to test like how it performs with on a convex function to compare, just like to show the baseline. So basically, and we test this. Those are for the high D, and in low D we test some of other like test functions in the standard benchmark database, like this drop wave and some Guannan, those standard functions. And we compare in the lower dimensional cases, we can compare with more methods, like for example the trust region based method or BFGS or trust region based method. You cannot really imagine it can go really high dimension, like 2000 D. And we compare with the standard evolution strategy. And one of the most popular ones is called the CMA ES. It basically do the covariance matrix adaptation. And add those strategies to the standard ES. And this method is pretty much dominating the area, even in the machine learning, in the reinforcement learning area. I mean, people use this method. And we can see for most problems that our method performs the best, except for this cross-entry method. We're doing good, but this is only 2D example. But this is the one of the functions that does not have any global structure. So even in 2D, we can see the methods are struggling with finding the global optimum. And in high D, I mean, we have some functions in high D behave similar to this cross entry, and then all the method will fail. So here is the test of our method to see if the convergence rate is independent of it's the number of iterations needed to get convergence is independent of the dimension. That's what we want to show, because we have the analysis for the convex functions. You can see for the sphere, which is a convex function, we can perfectly achieve that. And for Levé and the Ross-Trigan, from 10D to 1000D, we pretty much achieve it. The number of iterations is independent of the dimensionality. Because for Levé and the Ross-Trigan, those functions, even it has a lot of small fluctuations, but globally it has some good convex structure. Basically, it's a quadratic structure. But for the active function, it's different because the active function is very concave, and as we increase the dimension, the area or the volume of the flat area will dramatically increase with the dimension. And it takes us, even our method takes so long for our method to find the mode where the global minimum is in. So once we found the mode, then it converges very fast, but it will take very long to find the mode. And that's why we cannot see this dimension independence for this active function. So at least we found a reason why that's the case. And for the 2000 dimensional cases, we compare with other like ES method or CMA ES method and the BFGS method as a standard benchmark. And we couldn't really run any like a trust region or Bayesian optimization because those methods are not designed for real like problems like in that dimension, in 2000 dimension. So for for the convex function, clearly like BFGS will win, no doubt. But our method performs better than the other evolution strategy. And for when we move on to this non-convex functions like Ackley, Levy, and Rastrigen, you can see our method performs much better than the others. BFGS just doesn't work, and all the other methods are stuck in some local minimum here or there somewhere. But our method can always capture the global structure by doing the right amount of smoothing and capture the global structure to find the global minimum. And this is just a showcase of the example of the real world like a rocket shell design problem. Basically, they want to design a shell, and they use the finite element method to simulate to map from the design parameter space to the objective function space. So here, the only point of this example is to show, okay, in engineering applications, those finite elements simulation are really expensive. Basically, we only consider a simplified case. A real example, each simulation or function evaluation will cost like a couple of hours, even more, to run. So which proves the point that if we can parallel those runs, which will be very valuable to reduce time to solution. So which is another motivation of our method. Anyway, so I need to speed up a little bit since we're kind of. So another set of example is reinforcement learning. Basically, reinforcement learning is like we have an environment that we want to control. Reinforcement learning to me is just like a generalized control problem in the sense that we cannot derive adjoint equation anymore because the environment is too complicated, is a black box. And also compared to a classical control problem, the controller, now we call it agent, is much more complicated. Now we use a neural network to be a controller. So that's why the RL, or reinforcement learning, is a generalized control problem. And so we can use reinforcement learning framework to solve some classical control problems, like those carpool or those pendulum classical control problems. And also we can use reinforcement learning to solve this robotic control problem, robotics problems. That's what we showed in our experiments. So basically, in reinforcement learning, we have an agent that takes sequence of actions in the environment, and then we use this, put this action as the input into the environment and see how it goes, and and then the environment give us the output, which is the observation, and the feed the observation into the agent and produce another action. By doing several iterations, a lot of iterations usually, then we can assess the performance of the agent by defining a proper reward. And what reinforcement learning does is you want to train this agent or the neural network to maximize the reward. Basically, you can see why in the black box optimization, because when you take derivative or gradient of the reward with respect to the parameters in the controller or agent, you need to go through this environment, which is a black box. Of course, one way to do it, if you don't want to use black box, you can convert your environment to using some automatic differentiation tool if you can afford that cost. But you know, AD is not really like there's no generic tool, AD tool that can be applied to any code. Each AD tool have very strict requirements on the structure of the source code. So the code conversion is really not a trivial task. That's why people turn to use like a black box optimization to train neural network, to train the agent. So if someday there is a generic AD toolbox that can be applied to any software, then probably we don't need this black box thing at all. So yeah, in this reinforcement learning, people use, like, for example, people develop a gradient information or like a policy gradient and develop several other methods to solve this optimization or training problem. And the evolution strategy really plays an important role in this regime. In fact, each reinforcement learning training task will take hours, even a day or multiple days to finish for those complex examples. And the reason why the evolution strategy got popular is because OpenAI in 2017 put out a paper or some results on scalable training of reinforcement learning, some reinforcement learning benchmarks, and reduce the time to solution from like hours or days to like minutes. So that's why the evolution strategy becomes popular again in the reinforcement learning. So here in our test, we compared, we test our algorithms, compared with the 6 other training algorithms like ES or some improved version of ES by introducing some dimension reduction, and also some standard ones like the PPO, the TRPO, the DDPG, and a better version of DDPG, people call it TD3. Those are the benchmarks, the baselines that people compare. So here there are 2 sets of examples. The first one is kind of a simple ones, like can be characterized as the classical control problem, like the mountain car, pendulum, and the carpool. We can see, we compare the award growth versus this number of iterations in training. We can see our method converges faster in general than the other baselines, especially for this mountain car. This mountain car shares some similar features as the Ackley function. Basically, it has a very flat base and with a very sharp mode that includes the global minimum or a good minimum. Here, I would say we don't know where is the global minimum. We just see if we can find a better minimum or maximum, I would say. So we can see before other methods is struggling with around the score 0, and our method already captured the right mode and to find the global minimum or find the minimum, a good minimum, with a very small number of iterations. And if I keep plotting the growth of the reward, at some point you will see the other 2 will catch up, but in the much later, I remember it's like in 5,000 iterations it will catch up. But here we only plot to 500 iterations. And these 3 are these robotic control problems like the hopper, the invert pendulum, and the reacher. Those are, here I just want to show, okay, with a limited number of iterations, like 400 iterations, our method performs better than the others. If you give all the method enough time, they will eventually probably all catch up. But this number of iterations is really like directly determines time to solution. So that's what we want to reduce eventually with the help of a supercomputer. Oh, here the last figure I think I have is just to show the effect of the smoothing radius. Basically, if we choose the radius to be very small, basically we don't have any smoothing. In fact, our algorithm purely approximate a local gradient. We can see for this reinforcement learning tasks, our method performs not very good. But as we improve or increase the smoothing radius, so since our method can smooth out some local fluctuations, capture the global structure, so we can see the improvement of the performance. And also, you can see less fluctuation. Okay. To summarize, So we were motivated by the fact that standard ES method need to approximate high dimensional integral, and we develop a new operator to reduce to a bunch of low dimensional one-dimensional integrals, which are much easier to approximate. And then we use our operator into some together with the gradient-based method to solve optimization problem, non-convex case, and also some reinforcement learning problem. So as what I said during the talk, our method works for the problems or the loss landscapes that has some global structure, but perturbed or polluted by a lot of local structures. But if there's no global structure, then our method won't work. I want to emphasize that because there's no method that can solve all the global optimization problems. And another aspect that I want to emphasize is there is some hyperparameter tuning tasks in our algorithm in order to get the optimal performance. And in this talk, the result presented in this talk, we just manually adjust those hyperparameters. But right now we are working on establishing some adaptive strategy to, like, for example, what atoms do to the learning rate. And we want to introduce some similar strategy to adaptively adjust the exploration, the radius, basically the variance of the Gaussian smoothing kernels. For example, we don't need to do isotropic smoothing in all directions. We can choose to smooth more in some important directions, or do less smoothing in some non-important directions, or something like that. That's what we are trying to work on. And also we are testing the performance of our method on more complicated, like reinforcement learning problems on the Oak Ridge supercomputer to really compete with some scalability results that OpenAI put up. So I think we already see some good results. I think we can achieve a faster convergence or training than what OpenAI did. So here is the main references. Thanks. Any questions?
Thank you, Dr. Zhang. The floor is open for questions. I have the first one here. I'm going to read it for you. Do you also show that DGSES method can be scaled to a large number of parallel workers, or I'm guessing systems?
Not in this talk, but that's what we're working on right now. We're testing our algorithm on the Oak Ridge supercomputer. So basically, if you look at the algorithm, our algorithm, other than we do deterministic sampling, like using Gaussian quadrature, all the samples are deterministic, or there's no communication needed so basically we can just send those samples into different workers and let the workers, or let the different CPUs, the processor, to run them independently. And another thing is we don't need to even coordinate the random seed, because those samples are independent, are deterministic. So yes, I don't know if that answers the question.
Okay, thank you. I think Juan wants to ask you a question. Juan, go ahead, please.
Thank you. First of all, great presentation. It's an enlightenment.
Thanks.
I enjoyed tremendously all the slides and your explanation. Very clear, very nice. This algorithm is very similar to something.
I can't hear you. It's like
Let's see. Let me make sure. Give me a second. Sometimes this computer uses
it's like on and off.
Juan, maybe you can type your question, please.
This microphone? Can you hear me?
I can hear you better. It's
like
a noisy. It's a little noisy. Yes.
Yeah, if you can you please type the question? I can read it to him.
Oh, I have the chat window open, so I can just read it.
In the meantime, if anybody else wants to ask a question.
I have a quick question. Can you guys hear me?
Yes.
Okay, so I had a question. So since this method builds on top of a genetic algorithm base, do any changes or any additional methods that are implemented to the genetic algorithm, do they affect or conflict with this algorithm's effectiveness?
I missed the important word. Do they affect the complexity or something? Because I just there's noise at that spot. I
So
didn't.
additional methods to the genetic algorithm like speciation or additional variations that you can implement, do they conflict with any of this algorithm's methodology?
No, I mean basically, I mean you were talking about the population-based like a genetic algorithm, but here we're talking about this you know called we call it the surrogate gradient based like evolution strategy based on Gaussian smoothing. So it does not conflict with the other method. Actually, we compared our algorithm with the other method not for reinforcement learning because really not many people are using this genetic algorithm to train reinforcement learning. We compared it with some optimization tasks, like in quantum computing, some quantum computing problems that people work at Oak Ridge. So we found them and test the performance, compare our method with the genetic algorithm they use in their setting. So I don't quite understand their problem, quantum computing problem, but our method did perform better than the classical genetic algorithm. Of course, I don't know what version of a genetic algorithm they compare against because that's something in their library. So
Okay.
so
Cool.
yeah, so there is no, I mean, basically we're not implementing our algorithm in the context of the population-based genetic algorithm.
Right. Okay. Thank you.
Let me see the.
Dr. Zhang, you can read the next question.
What about scalability into more complex calculations such as MHD in the release testing such as plasma? Yeah, so actually I have a project with the plasma physicist on solving this called the runaway electron problem in fusion tokamaks, and we collaborate with the people at Generic Atomics, with the D3D data, all this stuff. And I agree. So if the model is super complicated, for example, each function evaluation requires a cluster or supercomputer to solve, then I mean, I really don't know how to. I mean, then of course this will be very time consuming even for our methods. So what we can say is what I can say right now is, so at each iteration, so we cannot parallelize the sequential iterations of the optimization process. What we can do is parallelize the function evaluations within each iteration. So if there is a supercomputer that is powerful enough to handle as many function evaluations as possible within each iteration, then we can achieve that scalability. But if we need to use the whole supercomputer to compute even one function evaluation, then everything becomes sequential. That's all I can say, I think.
I had a quick question.
Yeah.
So you may have mentioned this, but maybe I just missed it. So for the smoothing radius, so I know that we usually adaptively tune the learning rate. So can you also, and are you also adaptively decreasing the smoothing radius so that you approach the global maximum very quickly, and then you get the local maximum at the end, or minimum, I mean?
So exactly. Once we need to decay both the learning rate and the smoothing radius. So at the initial phase that we want to use a bigger smoothing radius to capture the global structure, but once we get into the mode or the mode where the global minimum is, then we need to eventually reduce the radius to be able to convert to use finally to use the local gradient to get the convergence. So we put both the decay schedule on both the learning rate and the radius, the smoothing radius.
I had another question. Actually, it's in addition, it's building on the previous question that he had asked about the smoothing radius. I think it might be similar. So in RL, in reinforcement learning, there are sometimes, unlike the cardboard problem where you're learning on one time scale, there are sometimes problems which involve two time scales where one have shorter time scale responses and one have larger time scale responses. And if you have one smoothing radius or one fixed Gaussian set of parameters, they may optimize to time scale. If two time scales, how does this adaptive strategy for hyperparameter tuning fit to that?
Well, we have actually, that's a good question, but we haven't really thought about that. I mean, yeah, that's not but that's a good point actually.
Okay. And had one quick last question. Also in black box function optimization for the benchmarks, we know whether those black box functions are convex or non-convex. But in a case where we aren't aware of the nature of the box function, do you recommend this method, or do you recommend a previous method and then you should use this if you know it's convex or non-convex?
Well, I think if you don't know, then I think my first choice, I wanted to see how like BFGS, those fast method can give you, right? If I'm given a optimization problem that I don't know what's in there, so I will assume it probably is the convex. If I don't know anything, I will assume it's convex, and I will try some BFGS or some even faster method to see how it works. If it can give me because for those practical problems, you don't need to find the global optimum, right? You just need to find the optimal that satisfy your whatever the criteria that application people give you. So right, so I just say, okay, I just use the fastest method on a single machine to see if I can give him the domain scientist a good answer that they like. If they like, then we'll be done with it. If I cannot get good result with simple method, then I would gradually just see if our method can do it. So I mean, that's kind of like the logic I have when I work with a lot of domain scientists, like in physics, chemists, or material scientists. So that's kind of like my mentality when I start collaborating with them or have a problem given by them that I don't know any details about the physics. Okay. So yeah, I don't know if that answers your question. So
kind of. Thank you so much. It was really nice.
So thank you, Dr. Zhang. We have one last question that's in the chat, and we'll wrap up.
Yeah. The first yeah. Yeah, the parameters need to be adjusted. Yeah, I mean, there is a, so basically we're just defining another gradient operator. So, I mean, it's the motivation, I think, is the same if you talk about the connections. And I mean, the parameters, I don't know what kind of parameters they are referring to. I mean, I think the parameters, what we can see, the parameters is the linear rate is the important one. The number of Gaussian quadrant rules is another one, but the most important one is the smoothing radius. So we don't want to over smooth it because then we'll lose the momentum, and we don't want to under smooth it because if we under smooth it, we cannot overcome the local minimum. We're going to be stuck in the local minimum as well. I mean, so from that perspective, this is really the smoothing. The sigma is really the most sensitive ones, and so far we don't have an optimal solution or optimal solution to select this sigma. So in the talk, we just need to do some trial and error to find the best sigma. But in practice, when I work with those application people, so my mentality was like, I'd rather use a relatively big sigma to guarantee that I'd rather suffer from some relatively a little bit slower convergence, but want to make sure I can eventually find a better minimum if the function queries is not that expensive. So it's problem dependent. You know, if people give me a question with a very expensive like MHD or CFD code involved in the function evaluation, then maybe I'll change my strategy, because I don't have that much budget, computing budget to really spend to try. You know, if the model is simple, I have more budget, then I can do some trial and error. You know.
So let me just get there. If you have a time series, you're using this, how would influence that parameter?
Here.
You fix it and then keep changing it, or would that parameter evolve?
I can't hear it. I mean, it's like on and off, so I can't really hear the question.
So in the interest of time, what we'll do is Juan can connect with you offline.
Yeah.
Dr. Zhang, yes. And I think there is some common interest there. So thank you so much for a phenomenal talk. And this wraps up our spring AI seminar talks, but we are trying to get some more speakers to UTSA over the summer. So we'll keep you posted. And please reach out to Dr. Zhang if there are further questions. And the talk is recorded and it will be available on the AI Twitter channel as well. Thank you.
Thank you.